We will do a few examples on Fourier series. Let f of x be piecewise continuous on interval from negative L to L. Then the Fourier series of function f of x is Fourier series of f of x is a0 over 2 plus infinite trigonometric series, and from 1 to infinity an cosine of pi n x over L plus bn sine of pi n x over L, where an equals 1 over L integral from negative L to L, function f of x cosine of pi n x over L dx, and bn has a similar formula, but instead of multiplying by cosine, we'll multiply by sine of pi n x over L dx. We'll do a few examples now. Example, let function f of x be given to us by cases. It equals to 0 when x is between negative pi and 0. It equals to 1 when x is between 0 and pi. We want to find its Fourier series. Firstly, we're going to find a0. a0 equals 1 over L integral from negative L to L f of x dx. In our case, L equals to pi, so 1 over pi. 0 to pi, because then x is less than 0, function equals to 0. 1 dx, so we're going to get 1 over pi x from 0 to pi, so final answer is 1. So we concluded that the a0 equals to 1. Now to find an, it's going to be equal to 1 over L, negative L to L, f of x cosine of pi n x over L dx. Now L again equals to pi, so we're going to conclude that 1 over pi integral 0 to pi 1, because the way the function is defined. L equals to pi, so we're going to get cosine of nx dx, so we're going to get 1 over pi sine of nx over n from 0 to pi, and that integral equals to 0 because sine of pi n equals to 0 and sine of n equals to 0. So an equals to 0 when n equals to 1, 2. Now to find bn, we're going to use formula bn equals 1 over L. Similar to formula for an, the only difference is instead of cosine, we're going to write sine. So L again equals to pi, so it's going to be reduced to 1 over pi integral to 0 to pi. Because the way function is defined, it's 0 in interval from negative pi to 0. 1. Sine of L equals to pi, so pi and pi will be cancelled out. Nx dx. So we're going to get integral 1 over pi. Cosine of nx is antiderivative of sine of nx is cosine nx over n with minus in front, and we do it from 0 to pi, so it equals to 1 over pi. Substituting pi, we're going to get negative cosine of pi x over n. Substituting 0, cosine of 0 is 1, minus minus gives us plus. So final answer is, instead of writing cosine of pi n, we're going to write negative 1 to n plus 1 over pi n. And that is expression for bn. So we know what bn equals to, we know what an equals to, when n equals 1, 2, we know what a0 equals to. So we are ready to write down our Fourier series for function f of x. So it's going to be a0, which is 1/2, plus sum, and from 1 to infinity, an, which is 0, will disappear, and we're going to have minus here. 1 minus negative 1 to n over n pi sine of n x. That's the final answer for this problem. We have a following problem. Function given by cases. F of x equals to 0 when x is between negative pi and 0. F of x equals pi minus x when x is between 0 and pi. And we asked to calculate the Fourier series of that function. First thing we'll do, we'll calculate a0. So a0 equals 1 over L integral from negative L to L f of x dx. In our case, L equals to pi, so 1 over pi. Because function equals to 0 before when x is negative, so 0 to pi, 1, and function equals to pi minus x. Function equals to pi minus x dx. So we're going to get 1 over pi. Antiderivative of pi is pi x. Antiderivative of x is x squared over 2. We're doing it from 0 to pi. So we're going to get 1 over pi. Pi squared minus pi squared over 2. So we're going to get 1 over pi times pi squared over 2. So it will be reduced into pi over 2, which is going to be our value for a0. Now to calculate an. L equals to pi, so 1 over pi integral. Because function is defined in equals to 0 before when x is negative, so we'll do integral 0 to pi. Function equals to pi minus x. Cosine of pi and x over pi, so pi will be cancelled out, dx. So we're going to get 1 over pi, integral 0 to pi, pi minus x, cosine of nx dx. We'll do integration by parts with u equals pi minus x, v prime equals cosine of nx, then u prime becomes minus 1, and v becomes sine of nx over n. So we'll do integration by parts. So we're going to get 1 over pi, u times v, pi minus x times sine of nx over n, and we do it from 0 to pi, plus 1 over n, integral 0 to pi. It's plus because minus minus gives you plus, sine nx dx, because u prime times v. Notice that this equals to 0 because when we substitute in pi for x, we're going to get pi minus pi 0. Sine of 0 equals to 0, so once we substitute in x equals to 0, we still get expression equals to 0. So that expression equals to 0, so we can ignore it. antiderivative of sine of nx is cosine of nx over n, because we're taking derivative, sine is negative, so we're going to get it's from 0 to pi, substituting n times n squared, substituting pi for n, we're going to get negative cosine of pi n, substituting 0, we're going to get minus 1, so finally we're going to get pi n squared denominator, minus minus give us plus, I'll write 1 in front, minus negative 1 to n, that's the same expression as cosine of pi n, and that will be our an. To calculate bn, we're going to be using formula 1 over L integral from negative L to L, f of x sine of pi n x over L dx, so it's going to be equal to 1 over pi integral from, because function equals to 0 on interval when x is less than 0, so we're going to calculate integral, switch on integral from 0 to pi. Function equals to pi minus x when x is positive. L equals to pi, so pi will be cancelled out. Sine of nx dx, and we'll do this integral by parts. We'll do integration by parts. We're going to omit the details here. Calculation is going to be similar to what we did in the previous case, and we're going to get 1 over n. So what we obtain is bn equals to 1 over n when n equals to 1, 2, and so on. A0, recall we did calculations just a minute ago, equals to pi over 2. An equals to 1 minus negative 1 to n over pi n squared. An equals to 1 minus negative 1 to n over pi n squared when n equals 1, 2, and so on. So we're ready to write down Fourier series for our function f of x. It's going to be equal to a0 over 2 pi over 4 plus infinite series n from 1 to infinity an 1 minus negative 1 to n over pi n squared times cosine of nx plus 1 over n sine of nx. Now, if we calculate the first partial sum for Fourier series, we're going to get pi over 4. If we calculate the second partial sum, we're going to get pi over 4 plus 2 over pi cosine x plus sine x. Calculate the third partial sum, we're going to get pi over 4 plus 2 over pi cosine x plus sine x plus 1/2 sine of 2x, and so on. And we can try to graphically interpret what our Fourier series do. If I, for example, try to graph S3x, then the graph is going to look approximately like following. Then I'll try to graph S8x. It's going to look something like that. And then if I try to sketch a graph of S15, 15th partial sum of x, then I'm going to get something which looks like and then going up, and then going down. So what you notice is our function is going to be eventually approximated by Fourier series. If I try to draw my function in the green, that function is supposed to look something like this. You see, our function is going to be eventually approximated by Fourier series. So first approximation is not as good, but eventually we're going to get something which is pretty good and nice.